Time for the new stream. Day 13, guys. Going strong. Let me share the stream link. And streaming right now. We'll be going through the FSDP paper and then kicking off a new run and making sure we have everything we need for local runs. And we can plan for the bigger ones. Okay, guys. Good morning for those of you where it's morning, good day or good evening, depending where you are. Let's start. Okay. So first thing I wanted to do is just skim through FSDP a bit more, just as a warm-up for the day. By the way, sorry for being a bit late. I had to prepare a presentation for later today, and we also have Niels Heimas, director of machine learning at Cohere, coming later to our Discord server. So I just had to do all of that before the stream, and now I'm here. So let's start. Okay, let me just skim through these to-dos. Let me see whether there is anything else interesting. I think, so as I said, FSDP, then just pushing for the run and also playing with mine data. I think that's what we need to prioritize. Everything else is a bit lower priority. Curriculum learning, we'll see whether we'll need that for later, not for now, because now we're gonna scope down the set of languages we support. And then everything else here can come in later. See whether prepared data is processing. This is lower priority. Some debugging about mine data. Some logistics. So this is kind of the main stuff, guys. Okay. Let me open up the paper. Let me share the paper link. FSDP paper is here for those of you who are in the channel. Let's open it up. It will probably be complementary to the blog we read a couple of days ago, but there might be new stuff, so I just want to make sure we read it. It came out in April 2023. This is as a part of release for PyTorch 2.0. So yeah, let's skim through it. Let's first skim the abstract and the figures, and then we can go and see the whole thing. So it is widely acknowledged. So first, PyTorch FSDP experiences on scaling fully sharded data parallel. Okay. It is widely acknowledged that large models have the potential to deliver superior performance across a broad range of domains. Despite the remarkable progress made in the field of machine learning system research, which has enabled the development and exploration of large models, such abilities remain confined to a small group of advanced users and industry leaders, resulting in an implicit technical barrier for the wider community to access and leverage these technologies. In this paper, we introduced PyTorch FSDP, an industry-grade solution for LLM training, or large model training, not necessarily language. FSDP has been closely co-designed with several key PyTorch core components, including tensor implementation, dispatcher system, and CUDA memory caching allocator to provide non-intrusive user experiences and high training efficiency. Additionally, FSDP natively incorporates a range of techniques and settings to optimize resource utilization across a variety of hardware configurations. The experimental results demonstrate that FSDP is capable of achieving comparable performance to DDP while providing support for significantly larger models with near linear scalability in terms of teraflops. Hi Adib, welcome to the stream. Okay, so that's kind of the introduction. Let's see the charts here. FSDP algorithm overview. So here, okay, so you can see the sharding happening here, layer 0 through layer 5, and we only have half of the layers. So the half of the shards on this device, I guess. I'm not sure what they mean by unit 1 and unit 2 here. Is this like pipeline parallelism? I doubt it. And then during execution, gather full parameters, pass through layer 1 and layer 2, and then free peer shards, and then again gather full parameters. This is for the backward pass, and then free the shards, and then synchronize the gradients. Okay, forward and backward. Okay, that's roughly what we saw in the blog as well. Nothing new there really. Communication efficiency versus input size. Let's see, uneven input sizes. All gather base, all gather one number of elements uneven, all gather 10 to the 6 number of elements uneven. Time per all gather in milliseconds. Okay, so it seems this one is the fastest one, whatever this is. Yeah, awesome. Thanks for saying hi, man. Thanks for stopping by. See you later. So all gather base, all gather even, uneven, uneven. I'm gonna see what this means. What do they mean by uneven input sizes? Reducing input size. Total communication time in milliseconds. So number of elements per all gather, the higher it is. So like the bigger numbers are on the left here. The smaller ones are on the right, on the x-axis, and then the time explodes going there, reducing the input size. Let's see these plots. Full sharding across 16 GPUs. Okay, flat parameters. I know that FSDP does this flattening for some reason. And then they accumulate the biases and the weights, and they flatten them out. Sharding group, local shard, padding. Okay, because we have 0 through 11, I guess the 15th one doesn't get anything, so we just pad. Okay, rank, full sharding. And then hybrid sharding on 16 GPUs. GPUs are configured into 2 sharding groups and 8 replication groups. Let's understand what they mean by that. So 8 replication groups, 2 sharding groups. So I guess that's just data parallelism and model parallelism in the terminology of Megatron or deep speed. Sharding groups versus replication groups. And then overlap communication and computation. So here is how it looks like on the CPU, how it looks like, I guess, on the GPU. GPU stream sending data to the GPU from the CPU. So we start with we kick off all gather, then it happens here, and then we forward computation, then all gather again, then forward, and then I guess we are done. Parameter free. Okay, this is just how they dial the computation so that you don't have any bottlenecks, I guess, on the CPU or whatnot. Let's see else. What else? Is there any other interesting diagram? There are these ones here, and that's it. After that, we can dig into the paper. So model scale. Here we can see, well, we are operating roughly at this scale at the moment on my local machine, 615 million. We might be able to squeeze in even bigger models, but because I'm suspecting that we are using data parallel degree of 2, we can reduce that to 1 and maybe do model sharding, and then we can end up with slower but bigger model, or bigger batch sizes. We'll see. Full sharding, hybrid sharding, full replication, DDP. They're just contrasting these different approaches, and then the biggest on the y-axis we have teraflops per GPU, so the throughput. I'm not sure which GPU, but looking at the numbers, this looks like potentially A100 or something. GPT 175B backward prefetch. As the number of GPUs increases, without prefetch we are here with teraflops. With backward prefetching we get 175 teraflops, and going down with the number of GPUs a bit. Okay, rate limiter, number of machines, RegNet, T5, LLM, deep VIT, which is Vision Transformer, Google T5, and RegNet, which is just a visual backbone. Number of GPUs, let's see, what's this? P90 QPS, I guess the 19th percentile. Number of queries per second or whatnot. This is for inference probably. And then let's see here, number of 80 gigabyte A100s. So I assume they're just using A100s everywhere when they mention a GPU. And then teraflops, let's see what happens here. I guess this is batch size. We'll see exactly what these plots mean a bit later as well, but just getting some early impressions. Peak memory goes down as we are adding the number of GPUs. Memory footprint. Peak memory again. This is just for different models, I guess. For T5, 11B, GPT. Okay, let's skim through the paper, guys. Let's go back up here. Let's quickly skim through this because this is probably going to be mostly marketing speech. The magnitude of neural network models is growing at an unprecedented pace. Upon inception, set a new record. GPT-3 sets a new record. Exciting applications, they say, and then modern large-scale recommendation models can reach beyond 1 trillion parameters. They serve multi-billions of users a day. Okay, we need efficiency. Pipeline parallelism being one of the methods. Into stages and distribute stages across multiple devices where activations and gradients are communicated across stage boundaries. Then there is a tensor parallelism, or so-called model parallelism. Shards model parameters, conducts partial computation on individual devices, and communicates activations that require layer boundaries. Then there is this zero redundancy parallelism. Shards parameters as well, but communicates parameters on demand. Okay. To recover the unsharded form, and executes the model as if it were replicated on every device. That's what FSDP does pretty much. The aforementioned techniques have served as the fundamental building blocks to enable training of large neural networks across various applications. Nevertheless, two challenges still persist. Firstly, some of these methods are tightly integrated with specific model architectures, which hinder them from being utilized as a generic solution. Secondly, some of these techniques are built on top of rapidly evolving internal interfaces, which become vulnerable to changes in framework implementation. Therefore, it's more robust and efficient to have a native solution co-designed with the core functionalities of ML frameworks. Additionally, constructing such a solution in a composable and customizable manner could potentially facilitate the community's future innovations as well. Okay, this paper presents PyTorch FSDP, which enables the training of large-scale models by sharding model parameters. It is motivated by the zero redundancy optimizer from Microsoft from DeepSpeed, but with a revised design and implementation that is aligned with the other components of PyTorch. FSDP breaks down a model instance into smaller units and then flattens and shards all the parameters within each unit. Okay, the shard parameters are communicated and recovered on demand before computations, and then they are immediately discarded afterwards. This approach ensures that FSDP only needs to materialize parameters from one unit at a time, which significantly reduces peak memory consumption. Hence, we saw the peak memory diagrams down below. The design and implementation of FSDP faces the following challenges. User experience is critical for achieving broad adoption. When working on prior PyTorch distributed training features such as DDP, we observed that aligning the user experience of distributed training with that of local training can significantly lower the learning barrier. Techniques like DDP require the model to be replicated on every device, which implies that the entire model can be constructed on the target device. However, although FSDP can easily adopt DDP's API design, large models might not fit into one GPU device and therefore cannot even be initialized efficiently. Okay, so that was kind of the inherent limitation. It was only focusing on data parallelism, replicating the models as they are, just the copies or replicas, and then running on a portion of the whole batch. Hardware heterogeneity often exists in modern GPU clusters, whereby interconnects are partitioned into high bandwidth islands within each machine and low bandwidth mesh across machines. Additionally, there may be further hierarchical structures in the rack or pod levels. I mean, even at the GPU level, as we saw, like if you saw my blog on Flash Attention, obviously there are like different memory modules in a GPU, like SRAM, which is super fast. There is the VRAM, which is the slow and the scarce component. That's actually the main bottleneck behind deep learning. So yeah, it's both internally inside of the device as well as externally, that heterogeneity, however you pronounce it. Okay. Consequently, the design of FSDP must accommodate such heterogeneity and optimize accordingly. Resource utilization is usually tightly linked with capital and operational expenditures, especially for companies that depend on large GPU clusters to power their mission-critical systems. To ensure that GPU devices remain fully utilized during distributed training, it is essential to minimize downtime caused by non-computational operations. Okay. Memory planning plays a crucial role in large model training. Makes GPU memory block allocation efficient and transparent through caching. Frequent memory defragmentations can significantly slow down training, which becomes particularly acute when working with large models. In such scenarios, practitioners typically seek to saturate GPU memory as much as possible to accommodate the largest batches or models. However, operating near GPU memory capacity significantly increases the chance to trigger defragmentations. Okay. FSDP tackles the aforementioned challenges through a variety of techniques. Firstly, to improve the experience, FSDP introduces deferred initialization that allows users to create a model instance on a dummy device and record operations invoked during initialization. Then the model can be initialized and sharded unit by replaying the recorded operations on a real GPU device. With this technique, FSDP can provide similar user experiences as local training, while effectively scaling large models. Secondly, FSDP offers configurable sharding strategies that can be customized to match the physical interconnect topology of the cluster to handle hardware heterogeneity. Thirdly, although parameter sharding design inevitably inserts communications which might block computations and introduce bubbles during execution, FSDP can squeeze out bubbles using an abundant set of tools to aggressively overlap communication with computation through operation reordering and parameter prefetching. Lastly, FSDP optimizes memory usage by prudently restricting the amount of blocks allocated for in-flight unsharded parameters and suspending CPU execution if necessary. By prudently restricting the amount of blocks allocated for in-flight unsharded parameters and suspending CPU execution. Restricting the amount of blocks allocated for in-flight unsharded parameters. So I guess that means when you do the all-gather to collect the other shards for that particular layer or set of layers, you have some strategy of reducing the peak memory at that point of time. Okay. We evaluated the performance of FSDP on various models, including popular language models and recommendation system models. I guess that's very important for Meta, which is behind FSDP and which was behind PyTorch. Now it's kind of they changed the roof, right? Like it's now not under Meta anymore officially, but like obviously Meta has a lot to say there. So those models utilize up to 512 GPUs. Okay, the experiments show that FSDP can achieve similar performance to that of DDP on small models. Beyond that, FSDP can facilitate significantly larger models with near linear scalability in terms of teraflops. FSDP is currently a beta feature of PyTorch 2.0 release and has been battle tested by both industrial and research applications. To simplify the presentation, the rest of this paper uses FSDP to refer to the techniques in general and fully sharded data parallel to denote the Python implementation in particular. The remainder of the paper is organized as follows: background on some popular techniques, and then elaborate the system design and implementation details of FSDP, and then evaluations, and then related work, and finally related to FSDP but falls outside of FSDP core. Okay, let's see. We can skip the related work section, that's kind of always boring. PyTorch has emerged as a fundamental cornerstone, stores values in tensor objects, which are versatile n-dimensional arrays featuring a rich set of data manipulation operations. Every tensor object has an associated storage that is allocated on a specific device. When tensors only represent simple transformations such as reshape and split, they can share the same underlying storage. Each module describes a transformation from input to output values, and its behavior during the forward pass is specified by its forward member function. Okay, just some details about PyTorch. Such a module may feature tensor object as parameters, with the linear module being an example that contains both weight and bias parameters. During the forward pass, the linear module applies these parameters to the input to produce the output by means of multiplication and addition operations, respectively. As both the data size and model complexity continue to escalate at a staggering pace, the need for an industry-grade distributed training framework becomes increasingly imperative for applications built on top of PyTorch. This section elucidates the trajectory of PyTorch distributed training capabilities. Okay, model replication. Model replication approaches are designed to tackle high-volume datasets by scaling out and distributing computations across multiple devices. DDP is the first end-to-end distributed training feature in PyTorch that falls into this category. DDP's adoption has been extensive, spanning both academic and industrial domains. DDP maintains a model replica on each device and synchronizes gradients through collective or reduced operations in the backward pass, thereby ensuring model consistency across replicas during training. To expedite training, DDP overlaps gradient communication with backward computation, facilitating concurrent workload executions of diverse resources. So we've seen this, I think, when we were going through the blog, this overlapping between gradient communication with backward computation. So the thing here is, as you're going backward, instead of waiting for all of the replicas to go through the backward pass completely and then do the gradient sync operation, instead of that, as soon as you go through the, for example, last layer, you immediately sync the gradients. So you overlap the computation with, well, the communication between the GPUs with the computation of the backward. So that's what they mean when they say overlapping communication with computation. However, one conspicuous limitation is that DDP requires all model parameters, gradients, and optimizer states to fit in the memory of one GPU. So it's not sharding at all. Consequently, DDP is inadequate for supporting large models, which are critical for cutting-edge machine learning breakthroughs. So you can basically speed up things, but you cannot train bigger models. For example, when wrapping models with more than 1 billion parameters using a 40 gigabyte GPU device, DDP will likely encounter out-of-memory errors on each device. Okay, model partitioning. As the size of models grow, they may no longer fit in a single GPU. In such cases, a viable solution is to partition the model into smaller components and distribute them across multiple devices. Both pipeline parallelism and tensor RPC are along this direction. Pipeline parallelism involves breaking a sequence of layers into stages and feeding inputs to different stages in a pipeline fashion to optimize the utilization. On the other hand, tensor RPC provides a lower level toolkit that enables arbitrary computations to be executed on remote devices. While both techniques are capable of scaling large models across multiple devices, they either limit the model to a sequence of stages or require modifications to the model source code to insert remote computations, which can pose a significant obstacle to adoption. Moreover, many industrial training infrastructures only support a single program multi-data paradigm, which necessitates a simpler entry point to handle large models. Okay, that was model partitioning. I never heard of why remote procedure call, tensor RPC. I know what's tensor parallelism. I'm not sure what tensor RPC exactly is. Let me just see the paper quickly. Tensor RPC, is this the one? Distributed RPC framework 24. Reference 24. Was that the reference 24? Yes, it was. So that's some, I guess, PyTorch specific thingy. Okay, let's go to section on model sharding. In addition to partitioning, sharding the parameters of a model can also help reduce its memory footprint and support models with sizes beyond the memory capacity of a single GPU device. After sharding models, each rank only holds. Rank is just, I guess rank is almost always synonymous with a single GPU. I might be wrong, but I think that's how they always use this term. Each rank only holds, for example, I have rank 0 and rank 1 because I have 2 GPUs. Also, when you do like CUDA column 0 or CUDA column 1, 0 and 1 are basically the ranks. Each rank only holds a shard of the model parameters, which prevents it from performing the same computations as local training. To guarantee correctness, the training process needs to employ one or both of the following techniques: perform computations with parameter shards and communicate activations accordingly. So this is the model parallelism, I think, approach, because you communicate the activations, whereas FSDP communicates the parameters. With this approach, ranks never need to fully materialize any layer. Exactly. So this is model parallelism. You just keep the shard there, and then you communicate the activations. However, each communication will appear in the critical path as it is inserted between 2 consecutive computation operations. As a result, this communication cannot easily overlap with computations, okay, unless off-path computations or computations from other iterations can be reordered to bridge the gap. Performing the same computation as local training by communicating parameters on demand before computations. That's the second way. This is FSDP, how they do it. Since parameter communications do not have any data dependency on preceding computations, they can overlap with computations performed in the same forward or backward paths. However, this approach requires that the forward and backward computation of each atomically materialized unit fits in the memory of a single GPU device. Okay. FSDP, as I said, falls into the second category of communicating parameters. Based on our observations and experiments, this approach is sufficient to support the vast majority of applications today and in the near future. It is worth noting that if the requirement of fully materializing each parameter unit on GPU becomes a blocker, we can further combine both techniques to support such use cases. Okay. Let me just think for a second. Performing the same computation as local training by communicating parameters. Since parameter communications do not have any data dependency on preceding computations, they can overlap with the computations performed in the same forward or backward paths. Got it. So you can basically be, imagine you have like a layer 1, you already have unsharded, so you have all of the parameters on your device for that layer. You start doing the computation, and in parallel you can start communicating the shards for the next layer. And once you get to the next layer, you basically free up the previous layer's redundant shards, and you start computing here. So that's what I mean by the overlap again between communication and computation. System design. FSDP is capable of scaling to accommodate large models that may not fit within a single GPU. More specifically, FSDP decomposes the model instance into smaller units and handles each unit independently. Okay. During forward and backward computation, FSDP only materializes unsharded parameters and gradients of one unit at a time. We have to see what the unit is. And otherwise, it keeps parameters and gradients sharded. Let's read it again. So during forward and backward, FSDP only materializes unsharded parameters and gradients of one unit at a time. And otherwise, it keeps parameters and gradients sharded. Okay. The memory requirements for FSDP are proportional to the size of the sharded model plus the size of the largest fully materialized FSDP unit. Okay, makes sense. Figure 1 demonstrates the overall workflow using a simple 6-layer model. Okay. Suppose FSDP decomposes the model into 3 parts. Layer 0 and 3, layer 1 and 2, and layer 4 and 5. The decomposition behavior can be controlled by user-defined functions. FSDP then wraps each of these 3 parts into one FSDP unit and shards parameters accordingly. Okay. To ensure correctness, FSDP needs to recover the unsharded parameters before corresponding computations. Let us consider FSDP unit 1 to explain this process. Before forward computation enters layer 1, FSDP collects the unsharded parameters for layer 1 and 2 by gathering shards from other peer processes. With the unsharded parameters, FSDP runs the local computation of those layers and then frees the peer shards it just collected to reduce the memory footprint. Therefore, during the entire forward pass, FSDP only needs to fully materialize one unit at a time, while all other units can stay sharded. Okay. Similarly, during the backward computation, FSDP unit 1 recovers the unsharded parameters for layer 1 and 2 before backward reaches layer 2. Okay, so before we reach layer 2 in computation, we start unsharding. When the Autograd engine finishes the backward computation of these 2 layers, FSDP frees the peer shards and launches reduce scatter to reduce and shard gradients. Again, this is overlapping gradient computation with backward pass. Gradient communication with backward pass. Hence, after backward computation, each rank only keeps a shard of both parameters and gradients. FSDP offers a wide spectrum of optimizations and knobs to account for diverse model structures and hardware capabilities. The remainder of this section delves further into the intricacies of model initialization, the sharding strategies, the communication optimizations, and memory management, which are all critical components of the FSDP's underlying design. So again, here it is. We gather before entering layer 1 and 2, then we do the computation, then we free up. Same here, we gather before we get here with the computation, then we go and do the backward pass, then we free it up, and then we synchronize the gradients, and then we continue to layer 0. Okay, model initialization. Before the advent of FSDP, PyTorch mandated the full materialization of the entire model instance on one device. Although users can allocate different submodules to different devices, this would require modifying the model source code, which may not be feasible, particularly if model authors and application developers belong to different parties. To facilitate a smooth transition from local to distributed training, FSDP must effectively aid in the materialization and initialization of a massive model, which poses 2 challenges. How to create a model instance without materializing any tensor storage, postponing initialization until a storage on a concrete device is attached to the tensor. Okay. Until a storage on a concrete device is attached to the tensor. How to ensure accurate initialization of model parameters in line with the user's implementation, even when the model is too large to fit on a single GPU. Okay. How to ensure accurate initialization of the parameters and how to create a model instance without materializing any tensor storage. To overcome the first challenge, we have introduced a mechanism called deferred initialization, which involves the allocation of model parameter tensors on a simulated or fake device. During this process, all operations performed on the tensor are recorded. Subsequently, when the tensor is moved from the fake device to a GPU device, all recorded operations are automatically replayed. By adopting this technique, users can generate a model instance from any third-party library without allocating any GPU memory blocks, while still accurately capturing their parameter initialization implementations. As illustrated in figure 1, once the FSDP has wrapped the model, it is evenly distributed across all GPUs, with each device holding only one shard in its memory. Therefore, in order to address the second challenge, each rank should ideally only materialize and initialize the shard that it owns. However, this is not always practical since we cannot predict what initialization logic the user will implement in the model init method. The initialization logic may rely on having an unsharded parameter on the device, which makes it impossible to shard the initialization. Consequently, FSDP must prepare the unsharded parameters before executing tensor initialization operators and simultaneously reduce the peak memory footprint. Given the sharding initialization is unsafe, FSDP applies the same approach as how it handles model forward and backward passes, i.e. initialize one FSDP unit at a time and shard the unit before moving on to the next one. Okay. When combined with deferred initialization, FSDP traverses the fake device model instance to decompose it into FSDP units, moves one unit to a GPU device at a time, and replays the recorded operations for tensors in that FSDP unit. Sharding strategies. The sharding strategy is a crucial element in FSDP that plays a significant role in determining the memory footprint and the communication overhead. It offers a variety of sharding strategies ranging from fully replicated to fully sharded. To generalize these sharding strategies, we introduce the sharding factor f as the number of ranks over which parameters are sharded. By setting the sharding factor to 1, FSDP fully replicates the model and simplifies to vanilla data parallelism that uses all reduce for gradient reduction. By setting the sharding factor equal to the number of devices, a global world size W, FSDP fully shards the model with each device only holding 1 over W of the model, where W is the world size. Hybrid sharding occurs when the sharding factor ranges between 1 and W. The remainder of this section focuses on full sharding and hybrid sharding, since the full replication strategy is similar to the existing DDP. Okay, so it's just a spectrum between DDP and model sharding of Megatron, and then you combine. So it's like 2D parallelism. If you know the 3D parallelism for Megatron, check out the paper if you haven't already. By the way, I made a video on this whole topic, so most of these things are already familiar to me. So I'm just trying to pattern match and maybe understand some additional differences. So for example, the new thing with the FSDP is that they're basically sharding the parameters and unsharding them on the fly, whereas Megatron is not doing that. Megatron just always has the same shard of the so just a single shard of the layer, and then they communicate activations in a smart way such that you have the equivalency of running locally in a single GPU and in that sharded fashion as well. So that's kind of the only difference I've seen so far between FSDP. Everything else is just like this is just like Meta's implementation of what NVIDIA and Microsoft and others have already done. Google as well. Well, Google is a different beast because TPUs and everything is internal and proprietary. Bunch of internal tools you cannot really use once you exit Google. Full sharding. The full sharding strategy leads to the lowest memory footprint, but incurs the most communication overhead. Therefore, FSDP must carefully organize communications to maximize its efficiency under this strategy. We conducted 2 sets of experiments to understand the impact of input size on collective communication efficiency. 2 sets of experiments to understand the impact of input size. What do they mean by input size here again? Results are shown in figure 2, which helped identify 2 ingredients: even input size. The NVIDIA NCCL library offers efficient collective implementations for all gather and reduce scatter that require even input tensor sizes across ranks. even input tensor sizes across ranks. Okay. I guess that just means when you're sharding the model, you have the number of parameters, the number of dimensions in the matrix needs to be just even, I guess. Well, and then larger input size for fixed communication volume, batching the data and issuing fewer collectives improves performance by avoiding the collective's launch overhead and increasing network bandwidth utilization. Okay, so that's why you want to go with bigger batch sizes. You want to minimize the amount of these reduce gather operations. Okay, for one, NCCL's all-gather API requires even input tensor sizes and writes output into one single tensor. PyTorch's process group wraps the NCCL API and enhances it by supporting uneven input tensor sizes across ranks and allowing users to provide a list of output tensors. The flexibility comes with an efficiency trade-off, as shown in figure 2a. We use all-gather base to denote NCCL's all-gather behavior, so that was the fastest one we've seen, and all-gather to denote the one that takes a list of tensors as outputs. The latter incurs additional copies between the individual output tensors and the consolidated single large output tensor before and after the communication. Moreover, for uneven inputs, process group mimics all-gather's behavior using group broadcast, which is slower than the native all-gather. In the experiments, we created artificial unevenness by moving one element and 1 million elements from rank 1 to 0 respectively. The results show that the native all-gather with even input size achieved highest efficiency. For 2, figure 2b fixes the total communication to be 2 raised to the power 30, which is close to 1 billion, FP32 elements, and varies the size per all-gather base. A smaller all-gather size means more all-gather invocations. Once the all-gather size decreases below 33 million, the total communication time begins increasing rapidly. You can see here 33 million and then explodes. Okay, so that means you have like what? You have to divide this number by 33 million to get the number of all-gather invocations. So that means you're increasing communication overhead, and thus the communication time explodes. Thus, to deliver high-efficient communications, FSDP organizes all parameters within one FSDP unit into a large flat parameter, where the flat parameter coalesces the communications of its individual parameters and also evenly shards them across ranks. More specifically, the flat parameter is a 1D tensor constructed by concatenating p flattened original parameters and padding on the right to achieve a size divisible by the sharding factor. To shard, FSDP divides the flat parameter into equal sized chunks where the number of chunks equals the sharding factor, and assigns one chunk per rank. The flat parameter's gradient inherits the same unsharded and sharded shapes from the flat parameter, and the flat parameter and its gradient own the underlying storage of the original parameters and their gradients respectively. Figure 3 depicts one example where we use one FSDP unit to shard a 4x3 NN linear layer across 16 GPUs. In this case, every GPU only holds one element from the flat parameter, with the last rank holding the padded value. This flattened concat chunk algorithm permits each original parameter to have arbitrary shape while minimizing the required padding to be at most f-1, reflecting its generality. Okay. Moreover, under this algorithm, the sharded and unsharded flat parameter and its gradient have the exact data layout expected by all getter and reduce scatter respectively. Okay. This enables calling the collectives without any additional copies for either input or output tensors. More formally, suppose for a model with psi number of elements, FSDP constructs n flat parameters with number of elements psi1 through psi9, psi-n, where the sum of these psi equals the total psi, the undindexed psi. Okay, for sharding factor f, the peak parameter memory contribution is in the order of big O, the sum number of elements over the factor plus the max. Because FSDP always keeps each local sharded flat parameter with size psi over f in GPU memory and must materialize each unsharded with size psi one by one during forward and backward. Since the first is fixed, the peak memory contribution is determined by the max. At the same time, the number of collectives per iterations is in the order of O of n. This evidences FSDP's memory throughput trade-off. Finer-grained flat parameter construction decreases peak memory, but may decrease throughput by requiring more collectives. Users can control this trade-off. So again, just trading off time and memory, the evergreen relationship in computer science. Users can control this trade-off by specifying how to wrap submodules into FSDP units. Okay, so that was the fully sharding strategy, I guess, or just a general takeaway. Yes, fully sharding. And then there is a hybrid sharding where you combine this with some amount of data parallelism. Okay. We refer to the strategy when the sharding factor is greater. By the way, this helps me tremendously when I'm later stepping through the code. Like I recall a bunch of these mentions from the papers, and that helps me then later check something or better understand what's going on. So if you're digging really deep into the model and trying to debug, all of this paper reading actually helps. So it's not just a fun exercise or whatnot. I have smarter ways to spend my time than to just do random stuff. That's not useful. Okay. Having said that, hybrid sharding. We refer to the strategy when the sharding factor is greater than 1 but less than the world size as hybrid sharding, as it combines both sharding and replication. Let me just see one thing. Talking about all of that, let me just open up FairSec. This is Stopes. Let me just reopen FairSec. If we go to long.json, replication count here is set to 1. So according to the terminology from this paper, that would mean we have DDP, data parallelism degree of 1. Replication count 1. It will be worth to understand what's this use local shard size. Let's check what this parameter is. Later, let me just... Okay, let's go back. So for global world size W and sharding factor F, the parameters are sharded across groups S1 through SW over F and are replicated across complementary groups R1 through RF, where each of these groups gives the ranks in the sharded or replicated group respectively. Aha, okay, so rank is a bit more general notion than just a single GPU. It's basically a group, it can be a group of GPUs. So like if you have two nodes with 8 GPUs each, and if you have like model sharding on a node and then data parallelism across the nodes, then this is rank 0, this is rank 1 when we are talking about data parallelism. But if you're talking about model parallelism, then you can have rank 0 through 7. Okay, yes. For gradient reduction, the single reduced scatter over all ranks becomes a reduced scatter over the sharded groups, followed by an all reduce over the replicated groups to reduce the sharded gradients. Okay, so reduce scatter over the sharded groups because you want to do the computation of gradients. That's why you have to do reduce scatter. And then you have to do the all reduce to sync the gradients across the models, across the devices. Okay. The equivalence follows from the decomposition, this one, where G sub R represents the gradient on rank R. Hybrid sharding can take advantage of data center locality for accelerated training and can reduce cross-host traffic to avoid as much contention in the oversubscribed environment as possible. At the same time, it provides a graduating trade-off between memory saving and throughput degradation, which is particularly helpful for models whose required memory footprint when trained with full replication is just slightly above the device capacity and do not warrant full sharding. Figure 4 shows one example. Okay. So you basically shard the minimal amount of times, which is just basically you have 2 sharding groups, but you do replication multiple times. Let me just think, how can one think about this? So you have 2 devices here, like 2 GPUs. Each of them has half the parameters, but each of them has the same sub batch. So you do the reduce scatter across them. You do a forward pass using that sub batch. And then once you have that, you can do the all reduce with the other replication groups, because you get the legit the valid gradients for this sub batch, and then you need to synchronize across the different replication groups. Okay, specifically data centers typically adopt a fat tree network topology with oversubscription, leading to abundant locality to exploit and a well-motivated reason to reduce cross-host traffic. Hybrid sharding can provide a natural mechanism to map the device mesh into the data center layout to exploit such locality. For example, consider a cluster as a group of W accelerators grouped into hosts of G accelerators each, where the communication among accelerators on the same host is much faster than the communication across hosts. We can set F to be equal to this to limit the all gather and reduce scatter operations within the same host, while creating a replication group for accelerators with the same local rank across hosts. Let me read that again. So for example, consider a cluster of a group as a group of W accelerators, like world size, grouped into hosts of G accelerators each. Okay, we can set this to this to limit the all gather and reduce scatter operations within the same host while creating a replication group. So like if W is maybe, W is like 16 and G is like 8, which is the usual configuration, like you usually have these 8 GPU nodes, then we can set F to be equal to 2. Or, let me think. Or is F the sharding factor? So that means this should be 8 and this should be 2. To limit the all gather within the same host while creating a replication group for accelerators with the same local rank across the hosts. Okay, for an M-size model, we can then compute the total cross-host traffic per GPU in the hybrid setup to be 2M times this ratio here, a drastic reduction compared to full replications, which is equal to this, and full shardings, which is equal to this. Okay, so these are two extremes, 2M, 3M, and then you have 2M and then G as the factor here. It's basically like a knob you have at disposal to trade off between peak memory and communication overhead. Additionally, since the all reduced collectives used in hybrid sharding operates at a smaller world size, they empirically achieve a better performance than invoking collectives at global scale in the case of full replication and full sharding, due to straggler effects and larger network interference. Another important design motivation for hybrid sharding is the needs for medium-sized models. These models are large enough to cause out-of-memory issues when trained with full replication, but are not large enough to fully utilize accelerator memory when used with full sharding, leading to both runtime overhead and memory waste. Because you're using too little memory per device and you're communicating too much. The hybrid sharding strategy creates a much richer memory throughput trade-off space by simply adjusting the F. Okay. Autograd. FSDP's flat parameter must interoperate with PyTorch's Autograd engine to ensure 1, correct gradient propagation, and 2, timely gradient reduction. For 1, recall that the flat parameter and its gradient own the underlying storage of the original parameters and their gradients respectively. Recall that the flat parameter owns the underlying storage. To achieve this before forward computation, FSDP sets the original parameters to be views into their unsharded flat parameter using Autograd visible torch split and torch view calls. Then the Autograd engine naturally allocates the unsharded flat parameter gradient and writes each original parameter's gradients to the appropriate offset as defined by the split backward function. For 2, FSDP registers a gradient hook that only runs once the flat parameter's gradient is finalized. The hook represents the post-backward logic and includes the gradient reduction. Notably, FSDP's approach builds on top of PyTorch's Autograd engine instead of hacking around it. As a result, FSDP automatically handles unconventional cases such as when not all parameters are used in the forward or when there are multiple forwards before a backward. So that's basically respectively mixture of experts and gradient accumulation. Or no. Gradient accumulation is when you go multiple forward, backwards, and then at the end you do the... Why would you do multiple forward? What changes across the multiple forward steps? Which model are we talking about here? This is probably just more for different classes of models, not necessarily, doesn't make sense for transformers maybe, but maybe diffusion models? I don't know. Okay, communication optimizations. The FSDP framework incorporates a range of native communication optimization techniques. This section unveils 4 major ones, namely overlapping, backward prefetching, forward prefetching, and accumulation. I think we know of all of these basically. Prefetching is basically what we said before. So when we are doing the backward pass, you prefetch the shards before you go and do the computation. Same for the forward. Accumulation is probably what I just said, the gradient accumulation, where you do multiple forward, backward, and you're not doing the gradient sync, which saves you the communication overhead. And then overlap is basically kind of connected with these two. Let's see. Overlapping communication and computation. The PyTorch C10D library offers the option for collectives to run in asynchronous with respect to the CPU and return work objects, where calling work wait blocks the CPU thread until the collective finishes. DDP follows this async collective and wait approach to overlap the gradient all reduces with backward computation. However, due to CUDA's sequential ordering semantics within a stream, FSDP cannot directly follow this approach to overlap its all gathers with forward computation. In contrast to DDP's backward, where the collective precedes the computation with which to overlap, FSDP's forward has the collective following the computation with which to overlap. The key challenge is that in PyTorch's eager execution, FSDP cannot know in general which flap parameter to all gather next, and hence the issue that all gather before the current forward computation. To address this, FSDP uses a separate CUDA stream to issue the all gathers, bypassing the sequential ordering semantics and allowing each all gather to overlap with existing GPU computation. As a result, FSDP's collective synchronization operates on streams, not simply work objects. Okay, again, some PyTorch details, but apparently it seems that the forward pass is the problematic one because you want to unshard the layer above, the layer that comes after the current computation layer. Figure 5 illustrates one example. Note that the backward pass contains one less all gather because FSDP intentionally keeps the outermost FSDP unit parameters in memory to avoid crashes in case there are any custom parameters falling in between FSDP unit wrap submodules. As a side optimization, both the reduce scatter and all reduce when hybrid shard is on can run asynchronously with respect to the backward pass, as they are not needed until the optimizer step. You know what's crazy, guys? All of the hardest work, engineering work in the world, everything is free. It's just like, it's crazy how we make our businesses. Like somebody, all of this hardcore engineering work is always free. Whereas things that are not that fun, like you have Jarvises of the world, where I think that's the name of the company, where they just make like literally a wrapper around this powerful AGI like model, AGI quote unquote, and you just earn tens or hundreds of millions of dollars. And then somebody creates this and it's just completely like, you can just go and see the code. Crazy. PyTorch process group represents a group of processes that can run collectives together. For NCCL backend, the process group NCCL implementation has one internal NCCL stream per device, where the separate internal stream is for asynchronous execution with the current stream typically running computation. FSDP enforces a single CUDA device per rank and uses a single process group for both all gather and reduce scatter, which means that its collectives run sequentially in the process group's internal NCCL stream. In the backward pass, FSDP issues the reduce scatter for the current flat parameter, and then the all gather for the next flat parameter. Hence, the single NCCL stream forces the reduce scatter to block the next all gather, which in turn blocks the next gradient computation and may become exposed on the critical path. FSDP offers backward prefetching to issue the next all gather before the current reduce scatter. However, as mentioned before, the key challenge for eager execution is knowing which flat parameter to all gather next. Fortunately for the backward pass, the reverse pre-forward order accurately approximates the pre-backward order, where the pre-forward order is freshly observed each iteration, meaning that the backward prefetching is compatible with dynamism across iterations. Okay, this is a bit above my pay grade. A lot of PyTorch specific details, NCCL and stuff. You have to actually go and dig into the code to understand everything here, but okay. Forward prefetching. For some workloads with relatively high CPU overhead, the CPU thread might not be able to issue the next pre-forward all gather early enough to efficiently fill the NCCL stream. If the model follows a static computational graph across iterations, then FSDP can assume the pre-forward order from the previous iteration and prefetch the next all gather even in the forward pass. This forward prefetching issues the next all gather before the current forward computation. Okay. That basically means you start syncing the... Wait just a second. Before you start doing the next computation, issues the next all gather before the current forward computation. Aha, got it. So before you start going through layer I, you already kick off the request for all gather for the layer I+1 to start unsharding the parameters. I guess that's what I mean. As I said, that's how I understood prefetching before as well. Gradient accumulation. FSDP offers two variations of gradient accumulation, with and without communication. With communication, FSDP still reduces gradients across ranks, and each rank saves the sharded gradients. Simply running multiple iterations without clearing gradients achieves this. Without communication, FSDP does not reduce gradients across ranks, and each rank saves the unsharded gradients. This latter variation trades off increased memory usage with decreased communication, which can increase end-to-end throughput. Memory management, runtime, limitations. Okay, before we get here, let's go to an easier part of the paper. Let's just kind of see the last sections here, and then we can go back. We have 1, 2, 3, 4 more pages. Related work, discussion, known limitations and how it can be combined with existing work. Further increasing scalability and efficiency requires FSDP combining with other paradigms. Pipeline parallelism. Okay, it seems it's hard to combine these two. Okay, so not really compatible with pipeline parallelism. Tensor parallelism. Okay. Presently, PyTorch provides a prototype feature called Parallelize Module that can be combined with FSDP to construct 2D parallelism. It works by organizing devices into a 2D mesh where PyTorch distributed tensor, d-tensor, manages tensor parallelism on one dimension, and FSDP applies sharded data parallelism on the other. Therefore, it's usually efficient to assign more expensive communications to interconnects. Okay, limitations. During our interaction with production and research, certain limitations, 2 tricky caveats. They're not readily apparent and pose significant challenges when it comes to troubleshooting. Mathematical equivalence. FSDP cannot ensure that it always achieves the same mathematical equivalence as local training. Especially when optimizers calculate per parameter metrics or global states. This is due to the fact that FSDP shards flatten parameters without respecting individual parameter boundaries, preventing any device from having a complete parameter tensor. As a result, optimizers cannot compute correct per parameter metrics, such as a norm. To address this issue, FSDP may need to shard unevenly or introduce additional padding, but this comes at the cost of communication efficiency. However, optimizing for metrics that require global states remains beyond of FSDP's control. Achieving this requires customized optimizers that leverage communications to calculate global states. Interesting. Not intuitive. And then shard the parameters. I'm not sure what they exactly mean by this. Like they do reconstruct. You have to unshard the whole thing. What's the due to the fact that FSDP shards flatten parameters without respecting individual parameter boundaries, preventing any device from having a complete tensor. Okay, complete as in you only have at most one layer materialized on a device or what? Okay. Share parameters. If anybody knows what they are saying here exactly, I think that's the case, but it's not intuitive. Why is that? Why can't you calculate global states? Okay. Sometimes PyTorch may raise an error message regarding missing tensor storage or size mismatch when using an FSDP rep model. This error can occur when an FSDP unit attempts to access parameter tensors shared with a preceding unit that has already been resharded. To address this issue, a straightforward solution would be to keep all parameters unsharded until the backward pass is completed using the Autograd up sharding strategy. If the model is too large to fit in memory, developers have to determine which submodules share parameters and consolidate them into a single FSDP unit. Conclusion: this manuscript elucidates the underlying rationale, design philosophy, and implementation of the fully sharded data parallel as of PyTorch 2.0. Attains usability and efficiency through a set of advanced techniques, including deferred initialization, hierarchical sharding, communication overlapping, and prefetching and rate limiting. All of these techniques are closely co-designed with other key PyTorch components to ensure the solution is sound and robust. Evaluations show that FSDP can facilitate large language and recommendation models with near linear scalability. Okay, three more pages to go. This is very much PyTorch specific after all, so it will not really directly translate to what we have in FairSec. Okay, memory management. PyTorch uses a CUDA caching allocator as a middle layer to serve GPU allocation and free requests for PyTorch programs. This design avoids frequent calls to CUDA-malloc and CUDA-free, where the latter incurs a costly device synchronization. Specifically, the caching allocator requests CUDA memory blocks and internally determines how to split and reuse the blocks without returning them to CUDA, with the goal being to reach a steady state without further calls to CUDA-malloc and CUDA-free. The caching allocator runs from the CPU thread, meaning that it must decide which caching allocator block to use for an allocation when the CPU thread processes the allocation request. It cannot wait until the GPU kernel needing the allocation actually runs, which may be much later. For a single stream, the caching allocator can directly reuse memory blocks by the stream sequential ordering semantics. However, for separate producer and consumer streams, there are no inter-stream ordering guarantees, and the caching allocator cannot be certain that a block is safe to reuse until the last GPU kernel, depending on that memory finishes running. Hence, if the CPU thread runs far ahead of the GPU execution, then the caching allocator cannot reuse blocks for the producer stream with pending GPU kernels from the consumer stream. Okay, too much information density and too little visualizations. FSDP allocates the altogether destination tensor representing the unsharded flat parameter in the producer stream. Okay, this is just too confusing. Let's continue to implementation. This section delves into the intricacies of FSD implementation, which, although do not alter the FSDP core algorithm, are crucial to understand before adopting FSDP. Users can access FSDP through two APIs: fully sharded data parallel model wrapper and fully shard module annotator. The former wraps the entire model and replaces submodules with corresponding FSDP units. In contrast, the latter installs FSDP logic as NN module forward and backward hooks, preserving both model structures and parameter fully qualified names. Initialization. Section 321 described FSDP's solution to efficiently initialize large models, which works well when submodule initializations are self-contained. In a rare situation where one submodule's initialization depends on a parameter from a different submodule, the on-demand materialization and record-replay approach might break if the parameter belongs to a different FSDP unit, because the unsharded version of that parameter could have been discarded to reduce memory footprint. Therefore, besides the advanced deferred initialization, FSDP offers two more options. Initialize unsharded model on GPU. The memory requirement for model initialization may be smaller than that for training, since training also involves gradients, activations, and optimizer states. Consequently, the training step cannot be performed on a single GPU device. Users might still be able to initialize the entire model on GPU and pass it to FSDP. Then optimizers should be instantiated after FSDP shards the model to reduce the memory footprint and align with the sharded gradients produced by FSDP. Okay. So basically, because during training you're using a ton of additional, you have to store a ton of additional data like gradients and activations and optimizer states, which are usually, especially for Atom, take like what, 12 bytes per parameter. So in case when you're doing initialization and you can just instantiate the whole model on a GPU, then you can do the initialization there, record the operations, and then go to FSDP. Again, just bunch of, this is too many details that are not really relevant until you actually start hitting any issues there. Initialize unsharded model on CPU. If the size of the unsharded model surpasses the capacity of GPU memory and can only be accommodated in CPU memory, it becomes impractical to move the unsharded model entirely to the GPU before handing it over to FSDP for parameter sharding. To overcome this challenge, FSDP adopts a streaming approach where the model is migrated to the GPU unit by unit. Upon arrival to the GPU, the parameters of each unit are immediately sharded, which in turn reduces the memory overhead before processing the next unit. This approach remains viable even when there are cross-module dependencies during initialization, given that all parameters of the entire unsharded model are present in the CPU memory. Okay. Note that both approaches above are subject to their own limitations. The first method entails the entire model fitting within a single GPU device and thus becomes infeasible for larger models. The second method, on the other hand, can handle larger models since the CPU has considerable larger memory. However, this approach may experience substantial slowdowns in comparison to deferred initialization due to the limited memory bandwidth and parallelization capabilities of the CPU. In light of these observations, users may still prefer deferred initialization even when dealing with models of the size range encompassed by the previous two methods. To delimit the scope of each FSDP unit, users may choose to employ the wrapper by intrusively applying it to submodules in the model source code. Okay, this is not really useful, the last couple of paragraphs. Let's just maybe skim through the rest because this is flat param handle. This is too specific to PyTorch. Runtime. Let's see what they say here. FSDP augments a local model instance by incorporating communication operations to reduce gradients and gather parameters. By incorporating communications operations to reduce gradients and gather parameters. Timely initiation of these operations is of paramount importance for ensuring both correctness and efficiency. Okay. Focus on backward. This is just how they implement the prefetching for forward and backward. Native mixed precision. FSDP offers versatile native mixed precision mechanisms. In terms of parameter management, it adheres to the standard mixed precision techniques, which maintains both low and full precision copies of parameters. Forward and backward computation use the low precision, and the optimizer step uses full precision. Permits user specified precisions. Okay, just skimming over all of this, not really something we'll remember. Users most commonly choose FP or BF16 as the low precision. Higher risk of overflow or underflow. However, the standard solution includes a gradient scaler that scales gradients to a safe magnitude. However, since FSDP shards gradients across ranks, a normal local gradient scaler implementation breaks mathematical equivalence, and instead FSDP provides its own sharded gradient scaler. Okay. Evaluation. This is the last part. We conducted an empirical evaluation of FSDP on large language models and recommendation system models and compared the results with those of DDP. Experiment specifications are described in the section 5.1. Okay. Experiment setup. In these experiments, we conducted evaluations on the Hugging Face T511B transformer, min GPT 175B transformer. Is this like Karpati's work or what? Min GPT. And finally, the DHEN recommendation model. The recommendation models consist of 768 billion sparse parameters and 550 million dense parameters, and were trained using FSDP on 8 to 512 A100 GPUs, interconnected by a 2 terabit per second network. They use a couple of other baselines and some different metrics they're using. Okay, model scale. We investigate the performance of FSDP when dealing with models of different sizes, spanning from 611 million to 275 billion, to make a comparison with DDP. Results with T5 models in figure 6a. The performance of FSDP and DDP is similar when evaluating the smaller models. However, DDP encounters an out-of-memory error when attempting to wrap models larger than 2.28 billion. So that's why this is the last point where we see DDP. In contrast, FSDP can effortlessly accommodate this model and achieve significantly higher teraflops by turning on bfloat 16. These experiments illustrate that practitioners can utilize FSDP for both small and large models and seamlessly transition across different model configurations. Then we conduct additional experiments to measure the acceleration attained through backward prefetching. Results presented in 6p. Prefetching 80% speedup. Throttle communications. In the subsequent analysis, we investigate the implications of throttling FSDP communications. Launching altogether too aggressively can lead to unnecessarily high memory footprint, as the CPU thread needs to allocate CUDA memory blocks when the communication kernel is added into the CUDA stream. This predicament may sometimes result in significant performance problems when the CPU thread runs too fast in comparison to CUDA streams. To gauge its efficacy in varying scenarios, we apply rate limiting to 3 different types of models and apply the maximum feasible batch size in each experiment. To gauge its efficacy in varying scenarios, we apply rate limiting to 3 different types of models and apply the maximum feasible batch size in each experiment. Okay. The results are plotted in C on plot 6C. One notable observation is that the rate limiter's effectiveness is not consistent, as it does not attain any speedups in the RegNet experiments and even impedes the deep VAT ones. This behavior is expected since throttling the communications can only boost training if the fast CPU thread aggressively allocates GPU memory blocks and causes defragmentation. If it is difficult to identify with certainty from latency measurements or profile traces, CUDA malloc retry can serve as a helpful indicator, which can be obtained from the number of alloc retries key in the Torch CUDA memory stats dictionary. The experiments conducted with T5 models have demonstrated that the rate limiter technique can greatly benefit training efficiency, yielding up to 5x speedups. Okay. So it's again very architecture specific, seems to be good for encoder-decoder types of transformers like T5, but for some reason not as good for the deep VAT, which is interesting because VAT is pretty much also a transformer. I'm not sure what deep stands for here for VAT. Therefore, before enabling rate limiting, practitioners should verify whether the fragmentation has taken place during training. So for RegNet, for T5 it boosts performance, and for the other ones it does not. Efficient training for larger models. To evaluate the capability of using FSDP for large models, we run 3 types of models using full sharding with prefetching and rate limiter turned on. Activation checkpointing and BF16 are also applied. Atom optimizer is used to reflect a production workload setup and to incur the costly 2 optimizer states per parameter. Okay, just some baselines and the setup. We further combine sharding strategies with 2 different configurations: rough, reshard after forward, freeze all gathered shards from other GPUs after forward pass and unshards them again before backward, and ref, no reshard, where the unsharded model parameters stay in the GPU memory after forward pass until backward computation finishes, which trades higher memory footprint for lower communication overhead. Okay. The experimental results in figure 7a and figure 8a indicate that FSDP is capable of accommodating the DHEN models on a large GPU cluster. When adding more GPUs in the cluster, the peak memory usage consistently decreases as a result of a decrease in the size of each rank's model shard. With 175 billion model, the experiments achieved more than 173 and 186 teraflops per GPU with batch size equal to 1 and 2 respectively, as shown in figure 7b. This is equivalent to approximately 55 and 60% of GPU utilization, given that the A100's peak is 312 teraflops per second, using the BF16 tensor core. Furthermore, the model demonstrated linear scalability from 128 to 512. Notably, with 128 GPUs, setting the batch size to 2 resulted in a considerably lower per GPU teraflops in comparison to other scenarios. This was due to CUDA memory defragmentation during the backward pass. The backward pass contributed 85.56% of the iteration latency for the 128 GPU batch size equals 2 case, while a normal backward pass only accounted for about 67% in these experiments. Using 128 GPUs is more likely to trigger defragmentation, as each GPU needs to accommodate a larger model shard. Figure 8 confirms this explanation, where the PyTorch CUDA caching allocator depletes all 80 GB of the CUDA memory as shown on the top left corner. And that's 128. For the GPT 175B. Finally, for the T511B models as shown in figure 8c, all experiments are executed comfortably below GPU memory capacity, while defragmentation are unlikely to happen. Nevertheless, as the number of GPUs increases from 8 to 512, a 7% regression in per GPU teraflops is still evident, as illustrated in figure 7c. This suggests that communications begin to outweigh computations on large clusters, and a near perfect overlap between communication and computation is no longer attainable. Okay, this is 154, 142. Okay, let's reread this last section. Yeah, this was a heavy paper because too many PyTorch specific details. This is just, there is not that many people who know all of this, and they mostly have built this into PyTorch. On the conceptual level, we could understand stuff, but they went too much into the actual, which makes sense. This is FSDP for PyTorch, PyTorch FSDP. Okay, with the 175 billion model, the experiments achieved more than 173 and 186, which we can see here. This is equivalent to approximately 55 and 60. That's a good utilization because you can never reach the peak. Furthermore, the model demonstrated linear scalability in terms of teraflops. Which affirms the efficacy of FSDP in handling large models with expensive computations or high-speed network interconnections. Notably, with 128 GPUs, setting the batch size to 2 resulted in a considerably lower per GPU teraflops in comparison to other scenarios. So 128 and batch size 2. That's the red curve, purple and reserved. Alek. This was due to CUDA memory defragmentation during the backward pass. The backward pass contributed 85.56% of the iteration latency for the 128 GPU batch size equal 2, while a normal backward pass only accounted for about 67, so that's because of the defragmentation. Using 128 is more likely to trigger the defragmentation, as each GPU needs to accommodate a larger model shard. Figure 8 confirms this explanation, where the PyTorch CUDA caching allocator depletes as shown on the top left. So here it is, 80 gigabytes. Okay, that's it for this beast of a paper, PyTorch FSDP experiences on scaling fully sharded data parallel. So a bit different compared to what Megatron, DeepSpeed are using and doing, but this is now the solution that's going to be in PyTorch 2.0, which means a lot of people are going to be using this. Although all of the big companies training big models have their own proprietary stuff, so they probably don't even care. So this is probably good enough for most people who will be using PyTorch 2.0 as it is. Okay, that was this one. Let me see whether there is anything interesting here. We have a couple more links opened up here. Getting started, how to use it. There's some good tutorials for this, which we don't need because we'll be doing everything in FairSec. Here's a bit more detailed explanation, visualization of how it works. Each process worker owns a replica of the model and processes a batch of data. Finally, it uses all reduced to sum up gradients over different workers. In DDP, the model weights and optimal states are replicated. FSDP is a type of data parallelism that shards model parameters, optimizer states, and gradients across DDP ranks. FSDP GPU memory footprint would be smaller than DDP. This would come with the cost of increased communication volume. Okay. Offload grads to CPU. CPU offload is enabled. This is during the backward pass. Backward local reduce scatter, then free the weights, and then offload the gradients to the CPU, potentially, just to reduce the memory. Okay. We don't need to go through that. Let's see whether anything interesting is said here. We're also going to make it easier to switch between DDP 01 and 02 and FSDP flavors of data parallelism in the new API. So they are supporting Microsoft's implementations as well. So we are using Fairscale FSDP. A bit of history on two versions. It was released in early 2021 as part of Fairscale. And then we started the effort to upstream Fairscale FSDP to PyTorch, making it production ready. We have selectively upstreamed and refactored key features from Fairscale, redesigned user interfaces, and made performance improvements. In the near future, Fairscale FSDP will stay in the Fairscale repo for research projects, while generic and widely adopted features will be upstreamed to PyTorch incrementally and hardened accordingly. Meanwhile, PyTorch FSDP will focus more on production readiness and long-term support. This includes better integration with ecosystems and improvements on performance, usability, reliability, debuggability, and composability. Okay. That was insightful. Was this published the same time as the paper? Looks like. No, even earlier. Let's read the intro here as well. Recent studies have shown that large model training will be beneficial for improving model quality. During the last 3 years, model size grew 10,000 times from birth with 110 million to Megatron with 1 trillion. DDP is a staple of scalable deep learning because of its robustness and simplicity. Allows to break this barrier. 0 and Fairscale FSDP. With PyTorch 1.11, we are adding native support for FSDP only as a prototype. Heavily borrows from Fairscale. Scaling tests of PyTorch FSDP on AWS show it can scale up to train dense models with 1 trillion. Realized performance in our experiments reached 84 teraflops and 159 for A100 GPU. Okay. Native implementation also dramatically improved model initialization compared to Fairscale's original when CPU offloading was enabled. Benchmark results, let's see this. Is this the same as what we saw before in the paper on AWS clusters? Is meta training on AWS clusters in general? Each cluster node is an instance of 8 GPUs, and internodes are connected via AWS Elastic Fabric Adapter. That's their protocol, like similar to NVIDIA's InfiniBand, but like much worse. GPT models are implemented using MinGPT. Okay. For the GPT 1 trillion, the maximum throughput of only 84 teraflops is achieved with batch size 4 and sequence length 128 GPUs. The use of A100 GPUs with larger memory capacity will mostly resolve this issue and also help scale the batch size to achieve much larger throughput. Did they use the 40 gigabyte versions? Or 80 gigabytes. Okay guys, let's remove this. That was the reading list. Just some context on FSDP, and now we are back to the actual code. Let's kick off the run. That's going to be the next task. Let's make a short break before this just to clear the brain after this torture, and then we can continue working on this. I'll have to stop probably around 3 p.m. so that's in roughly 2 hours, just because of the talk that we have at 4 p.m. with Niels from Cohere. So let's continue this after a 4-minute break. 4-minute break. Be right back, guys. Okay, guys, we are back. Let's go. Let me remove this and let's go to the training. So let's first understand this argument and then let's start kicking off the training. See how we can integrate Sacred Blue as part of the training, if it's already supported or not. Those are some details I care about. And then the goal will be to kick off a training run. I'm not sure if I'm going to stream with the training running in parallel because it takes a lot of bandwidth for streaming, so it might be a bit laggier on your side, but like we have to do it somehow. So let's start. Let's see first what this is. Okay. Let me just see whether we had any. We're waiting for Niels to join the server, so I might be taking a look at the server every now and then. Okay, let's go to the train script. Fairsex CLI train. Let's find this. Use local shard size. What's this one? Let's see what this one is. If true, use the training dataset size of the current shard only for sampling distribution. If true, use the training dataset size of the current shard only for sampling distribution. Not sure what that means. We'll see soon enough. Debug internal, okay. Let's see without the dashes. Let's see the underscore quickly. With the underscore, where is this used actually? If this is set, then we say using local dataset size of the current shard for sampling distributions. They just keep on pasting this sentence, but just because you repeat it doesn't mean it's clear. Okay, get train dataset sizes, total data size. Otherwise, the size is a sum across the shards. So that's how it's used here. Okay, multilingual data manager. And then total data size is used to do what? We can always put a breakpoint here to understand what's going on. And now let's see. Let's set up the training so that we can use our latest data that we computed in Stopes in the previous run. So let's see, in Stopes we have final data. Okay, prepare data. Under prepare data, process data new. Under here we should have the validation data as well. Let's just confirm that. Oh, that's a long list. Here's the validation data. Okay. So that's what we want to, let's copy the path to this one. And let's go to Fairseq. Let's go to launch JSON. find the train. Let's modify this from process data bin. We need to modify this such that we are using the latest path. So for that, let me trigger the training under the modeling directory. So let's go to modeling. Let's go to train here, train script. And in order to get those paths, data directory, we need to set, let's call the train script direct train fine tune, generate, interactive, train for the sweep, train for the local, direct train, okay. Wait, how do we call the, I forgot, I haven't used this one in a while because we're just shortcutting to train.py directly. Find the modeling train script. How is this one called again? Launch job. Aha, this one is set up using the config here. Okay. So for that, let's just open the config. And let's just open the fine-tune FP and let's just change the data set FP chat. So this one needs to be, instead of this, we need prepare data, process data new. Okay. And then let's kick off the run and just collect the sweep here. Okay, kick it off with no arguments basically, as far as I understand here. And then here's the data directory, data new all the way through 27. Whoops, let's just paste this to the terminal, copy this, copy this one, stop, go to launch JSON, go to the train local, and let's just replace the previous one. So all the way from here to here, we don't need that because we're gonna put in this one. And we have to put double quotation marks, and that's it. Okay. So this one uses the new data, which has both the train as well as the validation. And we're gonna save this to model checkpoints. Model checkpoints. Let's call it save directory new as well to be creative. Memory efficient. Max updates. Task language pairs. Okay, let's change the language pairs. And let's see how these are exactly used. So let's use the ones that we have in the validation set. And for the validation, let's check the stopes. Let's go to stopes. Let's go to prepare data YAML, but not here, instead here. Okay, so here are the directions we care about. English, Russian, and Turkish. UZN. English, Latin, Turkish. Like this. And then Turkish and then use it, and I think it was Latin as well. Double check. Stopes, again, Turkish Latin, use it and Latin. Okay, so that's the language pairs we want to use. Let's continue. Use local shard size, sampling method, temperature, criterion, label smoothing, max token seed, log interval. All of this makes sense. Languages, transformer, okay, we don't want to disable validation. We don't want to disable this. Okay, now we have validation actually, so we want to run the full thing. Okay, so let's see. Download a subset. Again, let's quickly skim this. I think this will be good enough. Now let's start kicking off. So the goal today and tomorrow will be to just have a training run, and we can track progress, and then we can refine which languages we want to train on. But we are now at the stage where we just have to start training locally and track the results and share the updates. Skipping valid size inputs, valid test. I'm not sure what this does. Memory efficient. All of this makes sense. All of this makes sense. We don't want to touch these for now. Learning rate, clip norm, dropout, weight decay, criterion, label smoothing, max token seed, log interval. This is all good. Validate max source position, max target. Enable M2M validation. I'm not sure what this one does. Add the prefix, share the embeddings, decoder normalized before, encoder normalized before, optimizer atom. All looking good. I'm not sure where we want to pass all languages here. Does this, what's the difference between language pairs and languages? That's one thing we have to understand. So what's the diff between langs argument and lang pairs? Also, what does this one do? So the goal is to understand every single parameter over the next day or two, so that we know exactly what's going on here. Save architecture, encoder, decoder, number of the internal dimension, decoder embedding dimension, encoder attention heads. Okay, these are just setting up train subset, validation subset. Makes more sense to put these together just to organize them easily. Like this. Rally, attention, drop. Makes sense to also organize these transformer arguments, like encoder layers, decoder layers, and then dimension, encoder embed dim, 1024, decoder embed dim, encoder attention heads. Okay, these are just specifying details about the architecture. Dropout. Okay. So this is just specifying the transformer with layers, with number of layers, the dimensionality, the number of heads, the dropouts. Okay. This just saves. How often do we save? Save interval, update, save interval. Let's put the lengths. Let's put this together with language pairs. Language pairs should be here. Okay. We don't really need this. Let's put it here. Beta. Save directory. Let's organize the atom arguments in the same place. Atom. All of these should be in the same place as well. Like this, and then I saw more of them. Decoder normalized before. This is also relevant to put it here. Normalized before. Share all the embeddings. This is also for the architecture. Encoder normalized before. That's also for the architecture. Maybe we can even separate just to make it a bit easier to parse. Like this. Okay, and then I've seen where is Atom, FP16 Atom stats, Atom optimizer. All of this should be right here. These are the optimizer settings. Optimizer arguments. This is also specifying the context length. This should be here. Just trying to organize these arguments now that we're trying to understand the training run. I'm not sure what this means. What's this mean parameters to wrap? 1, 2, 3, 1, 2, 3, 100 million. What does that even mean? And then there are the distributed settings like DDP, replication count. We need to understand what those are. Distributed arguments. What's replication count 1? checkbox. Replication count. What is that? What else? Let's organize these logging statements. Log interval, validate interval, log format. Let's just save all of those in the same place. Like here, log format, logging interval, interval updates, updates, intervals. These are all related. Max tokens. This is batch size, so okay, seed is just a generic argument. We can put it as the first one up there. Distributed world size, this should be here. Up there is the data and the seed. So for data, maybe we can put the number of tokens. So max tokens should be up there. This is the data arguments. Okay, and then there is the save directory. I'm going to put this one also here. Looking better. Memory efficient FP16. This one I think has impact on the optimizer. I'm gonna double check what it is. Okay. And then update frequency. This is just how often do we do gradient accumulation. So this is again more of an optimizer detail. Task. Can put that up there. Memory efficient FP16. We have this double. Max number of updates. This is just again optimizer stuff. How many steps do we do of optimization? Okay, keep interval, keep last, epoch, intervals, all of these should be here. Okay. Warm-up steps, warm-up learning rate, stop learning rate, all of this should be under the optimizer. Clip norm. This should also be under the optimizer, I guess. And then dropout and weight decay. Either this one could be under model and weight decay under optimizer, something like that. Does not matter that much. This one can be under optimizer. What's the weight decay? a regularization parameter. And then learning rate scheduler, again, this is optimizer stuff. Okay. Criterion and label smoothing. Best checkpoint metric. This should probably be under saving here for the checkpoints. Criterion and label smoothing should be under optimizers. Languages of interest. Let's put this all the way above there. Data. Okay, we are left with a couple more unclassified arguments. Add data source prefix tag. This is definitely the data argument. This adds the tagging tokens. Encoder length token is source. Again, this is not additional data argument. And then decoder length token as well is a data argument. Just specifies the tokens for the source and the target. Now, I'm not sure what all of these are. When you say sampling temperature and use and skip, we have to understand what these exactly do. In the context of training run. Okay. Looking good. The things, let's see, what do I do not understand? I don't understand the difference between these two. Let's see that. What's the difference between languages and length pairs? And then data arguments, this is fine, this is all fine. Skip invalid size inputs, what's this? Use local shard. I'm not sure what this one does. We put a breakpoint there. Sampling method, what do these two work? Is this, let's see what these do in the context of training. And then enable the validation. Minimum parameters to wrap, what does this do? Okay. Let's continue. Save interval update, save interval, log interval, validate interval, log format, where to save stuff, best checkpoint, keep. All of this is reasonable. DDP replication count. I'm not sure what replication count exactly does. Atom epsilon beta is optimizer. Memory efficient. Not sure what this one does. Let's check it out. Max updates, weight decay, learning grade schedule, updates, learning grade stop, clip norm. Okay, architecture, we know everything here. And that's it. Hello, Smith. We should put this one here. And then grab this one and put it here. Decoder size, this should be here. Number of heads, dropouts, attention dropout. Let's put the dropout there as well. Okay, guys, this is much more manageable now. We don't know what these are. Let's go and kick off the training run and understand these parameters exactly. And then we're gonna kick off the final run, the final quote unquote, the first one. And then in the background, we can decide on the languages that we wanna include into training. Okay, let's go to train.py under fairsec CLI directory, fairsec CLI, train.py. Let's kick off our run. But before we even run, I think we can see a lot of these just, you can just search for them and see how they're used. List of languages. How exactly are these used? Generate a list of languages, comma, separated, which can appear in language pairs. Okay, which can appear in language pairs. So then the question is, for the language pairs, we can always keep this. So we can always keep the lengths as the full set of languages we plan to support. And then the language pairs. Is there any mention of language pairs here? Language pairs. There is no mention of language pairs. Let's see. Do we just train for these directions or what? That's my assumption at the moment. Let's just validate that. Language pairs for multilingual training. Okay. We trade round robin over batches from multiple language pairs, order according to the language pairs arguments. In training order. Can these even be BCP47 format, or do we need the ISO 6391 format? Multilingual translation. Okay, I suspect I know what it does, but I'm not 100% sure that's how it's used. Okay, let's see, skip invalid size inputs. What's this? What's this argument about? Let's see it. Okay. We don't see any mention of how it's used. No mention of what it means. Skip invalid size inputs valid test. That's a very verbose name for something that doesn't really tell you what it does. Skip invalid, some skipping of invalid size inputs in the validation test. What exactly is that? Okay, some skipping. Let's only include Py files. So this is where it's used. Ignored. If ignored is bigger than 1, okay, let's see under instead of dashes, let's use the underscores to see where it's used in practice. Okay. Maybe we can remove this one as well. Or maybe not. Okay. Ignore invalid inputs. Aha. Ignore invalid inputs. That's where it's passed in exactly. In the ignore invalid inputs, ignore too long or too short lines, invalidation and test set. Aha. Skip invalid size inputs in validation and test sets. Let's see what this flag does when we enter the batch iterator. Okay, we can quickly kick off a run. Let's go here. Let's set this. Somewhere in the train step, we'll have this ignore being called. And let's see exactly where. Okay, process terminated because no such file or directory. Why? Data bin shard 0 dictionary English Latin. How come? New data bin shard 0. Why would we skip English? Unable to open. What? Oh my god, did we maybe change? This might be just broken symlink. This might just be a broken symlink. We can fix that quickly. Let me just see whether. Okay. I just have to send one quick email, guys, and I'm back to stream. Give me just a minute. Just need to send the presentation to the MIT folks quickly. Here it is. Attach. Okay, sent. So let's see why this is broken. Because this is a symlink. And where that is set in the prepare data at the very end in the binary stage. So here, so we go through all of the shards, and then we symlink target path. All of those should be symlinked to the original path. Oh my god, why is this not working immediately? Okay, there's a couple of things we can do. One is to just kick this off again and hope that everything is cached and we quickly go to the end. Or I can just try and manually, I can just manually go and map all of them to the same model. Okay, I know what happened, guys. I think I can quickly fix it by just copying the SPM models. So I deleted the SPM models from my FairSec root because I basically changed its location. This shouldn't be problematic to solve. Let's just see, filtering, prepare data, SPM models. I just need to copy these two. And I just need to copy them to the root here. Okay, so having done that, let's try and retrigger the run. That might be the easiest fix. Let's just go to FairSec CLI, train, run. Hopefully that fixes the issue. If not, I can go and manually change the symlink. That's kind of the next solution. Okay, it worked. So that was the issue. The symlink was pointing towards a path and I deleted that those two SPM models. And so, I mean the model and the dictionary. And so it was complaining. Okay. So we go through this and we just load the data set. Let me see how this is going to work in the background. Loading data. Okay, let's load validation, training set to true, epoch 1, shard epoch. Let's just enter here, hit F5, load multi data set, load split data sets, load data param list, get data paths and length pairs for valid. Let's see whether this is going to work nicely. Did it load my validation? It should have. Let me see, data paths are here. These are the locations to the shards, and then inside of those shards they'll find the validation prefix. So let's see, data paths, get number of shards for these two. Let's see this one. Let me actually quickly rerun, and I want to enter in this one as well. Just need to understand exactly. The first time that I'm running this with validation, I really want to understand why and how it's working. Kick it off again quickly. We can remove this breakpoint. Okay, let's go, guys. So get data paths. Okay, we've seen this. Split the paths. Okay. Wait. Load split data sets, and then we enter here. Get split data param list. And then data category main paths, all of the paths are there. We split the paths, we grab the shards dictionary. For the validation split in here. Get shard number. Yeah, we just have a single one for validation, that's true. We go through the files. If it starts with it, then we grab the direction, we pass in directions. And then going through directions, we just add for that direction. Okay. Let's continue here. Get dataset key for category main source to target. One. Repeat this. Exit. So we have one shard and one shard. That's exactly the case. That's exactly the situation. If you take a look at the Stopes library, here, data bin, shard 0. If we just focus on the validation ones, they are only here. So we have this English Latin to Russian Cyrillics for English and for Russian, and we have Turkish Latin to UZN language, and same here. So those are two directions we have. So that means we only have one shard in shard 0. Let's go. Split the paths. Get sharded data. Get the language tokens. Get the language directory directions. And then the same logic here. Get split data path. That's the shard 0 exactly. and then we add for English, Latin, Russian, 0th shard for validation. English Latin is the source. Grab the dictionary. Russian Latin category. Okay, this looks good. And then we add the second direction. Parameter list. We just add the second one as well. This is going to be for Turkish. Also same shard, but this time different source, Turkish, and use at end. Okay, let's exit here. Let's go out there. Datasets. We'll load the datasets for both of them. Okay. Okay, this should be good. And then we go through the datasets, split name, splits, and then we load them. Okay, looking good. Looking good. And we are done. We are here back in the main, and we've loaded our validation datasets. So let's continue. And let me now go back and see the language pairs. Where are these used? Let me see. We are looking to understand what these arguments, how these arguments are used exactly. Language pairs. Let's see. Args, language pairs. How is this used? Self language pairs. Eval language pairs are the same. Setup data manager. Load the languages. Okay. Let's see whether we hit any of these. Let's go back to the main execution. So I've set breakpoints there. Let me see also how is enable M2M validation used. Sweep train script. Let's just remove the dashes and make them underscores. Enable M2M validation. What does that exactly do? So if that's set and split is this and split exists, then we go, let's see, let's just put breakpoints there. So once we hit, we'll understand how it's used, hopefully. And then there's also the min parameters to wrap. what does this do? Minimum number of parameters for a layer to be wrapped with FSDP when training with DDP backend fully sharded. Smaller values will improve memory efficiency, but may make Torch distributed communication less efficient. Okay. So we have it set to like million. We literally have it set to what? We go to long JSON, I think it's around million at the moment. Actually 100 million. 100 million. We're at 600 million, so that means but for a layer, minimum number of parameters for a layer to be wrapped with FSDP. For a layer to be wrapped with FSDP when training with fully sharded. So if it's below this, we will not wrap it. So smaller values will improve the memory efficiency because we'll be wrapping stuff up, meaning we'll be sharding them using FSDP, but may make communication less efficient. Of course, that's the inherent trade-off of FSDP that we've seen reading the paper this morning. Set to 0 when checkpoint activations or offload is passed. Why is that? When we are checkpointing activations, okay, let's just see how it's called in the actual code. Again, convert to underscore. Model. What's the default value? Default value is precisely 100,000. 100 million. Transformer base. Okay, so it's an argument for FSDP wrap as we saw in the previous explanation. And then minimum number of layer params to wrap. If this is not none, then we go through the module, we grab the sum. If this is bigger, then we wrap, otherwise we do not wrap. Okay, got it. So this basically means that because we do cross with 600 million, we will be entering this particular, let's just put the breakpoint there. But I'm fairly sure I understand it now. It's basically like a threshold. After this point, after this scale, enable FSDP, basically. That's what it's saying. As you can see here, building the decoder layer. If it's not a mixture of express layer, or if this is true, then we wrap like this. Okay, so apparently it also goes, so the encoder has to be bigger than this to be wrapped, and decoder. So apparently encoder and decoder might be separately wrapped. So let's just put the breakpoint here as well. And let's put the breakpoint here as well. Let's continue legacy. Yeah, okay, we can kick off the training again. Let's also see, while we're here and we're setting breakpoints, we're in the business of setting breakpoints now. replication count. Let's see how replication count is used exactly. Is this the data parallel setting? Is this the data parallel degree replication count? How many times we have to replicate the model? That's my understanding when I hear this name. Let's just replace dash with the underscore. Train script, checkpoint, replication count. Load the checkpoint with the replication count. Let's put breakpoints there. Replication count. Replication count. Aha. Replication when loading mixture of expert states. This is probably only relevant to, I think this is probably only relevant for mixture of expert models, potentially. But then why don't you just put a prefix like MOE so that I know this is only mixture of expert specific? That's why I'm still thinking it might not be specific to mixture of experts. Okay, we've set some breakpoints, and then there is the final one here, memory efficient FP16. That's probably set somewhere in the optimizer. So FSDP always uses memory efficient wrapper mostly for the grade scaling, but if we don't have the enabled, then we are effectively doing regular FP16 and can allow the use of optimizers that would otherwise be unsupported by memory efficient. Okay. The Fairsec version cascades and params to FP32 internally to support memory efficient FP16. Okay, let's see without the dashes. Let's see the underscore. Allow unsupported. If it's memory efficient, then this is not allowed. Build the optimizer. Memory efficient optimizer. Let's just put the breakpoint there as well. Use a memory efficient version of FP16 training implies that this is also used. Mixed precision, CPU offload. If memory efficient, FP16 that we push to CAF. So then the question is, why not always use this? Why isn't everything just memory efficient always? Okay, so guys, let's now rerun. Let's just see a couple more things. Actually, sampling method. What is sampling method for the training? Let's just put this to underscore sampling method. multilingual dataset manager. Okay, let's put a breakpoint there. Sampling method. Aha. Get batch iterator. I think this sampling method might have to do with how we sample. I'm not sure. Let's just okay. And then sampling temperature 1. Martin said, could it be tied with the machine where the model is supposed to be trained? Would it be possible for some machines not to be a good fit for this particular memory optimizer? I don't see how this is hardware dependent. This is more optimizer dependent. Some of them support it, some of them do not. I saw Adam supports it, but like maybe Autograd, like some of the other ones were not supporting. If you're referring to the memory efficient FP16. Anyhow, let's kick off another run. Go to train.py again and rerun it. Let's see where we hit the first breakpoint. Okay. So the first thing is sampling method here. So during the construction of the multi-simple epoch task, translation multi-simple epoch task, we pass in the sampling method here. But this one is actually built. Is there do we pass the sampling method here? Yes, temperature. Maybe in the build sampler here. Return the sampling method. Okay. Build the sampler. So we just pass and save it. And then during the, okay, so this, in the next step, I guess we're gonna set up data manager. Okay, let's just hit F5. Set up data manager. Let's just enter here again. Okay, it has something to do with data. Sampling method. Okay, let's hit F5. This is the second. Okay, we now hit this because we're in the build model. So from main, we entered in the build model. We're building the model. We're building the transformer, and now we're building encoder. And inside of encoder, we have this logic. Build encoder layer. Aha. Well, if it's just about a layer, that one will not be wrapped. Aha, so it's probably just, okay, this is just some recursive definition, got it. So otherwise, if even the layers were above 100 million, then it would be wrapping those. Otherwise, it's gonna wrap up only in the top level of the model. So here, we enter here, and this is again, as I said, 100 million, and this is just a small layer that certainly doesn't have. I'm not sure how we can easily compute the. Can we have access to the weights here? Nope. This is certainly smaller than 100 million. So when we enter here, the sum will be what, like 2 to 4, 12 million. So it will not return, as you can see, it's not returning. Okay. So it's just a plain layer without wrap. Hit F5. Again, same here. So let's see when we actually hit this. Build decoder. Same logic here. If we enter here, it's not gonna hit this because it's smaller. 16 million, a bit bigger, but still smaller. We can remove this. Okay. Okay, and now finally, we are already in the low data set. So apparently, we did not wrap it any of the modules, but we did. If we go to the main one, if we go to the main function, because of this, where is the build model called here? Build model, we wrap it with a context here. So the top level model is going to be wrapped, but the layers itself will not be wrapped, as none of them hit this particular branch. Let's again see build model. So does this one just default wrap it? Group. Config. And then with enable wrap. Fully sharded data parallel. Okay, let's see where we are. We are now just hitting some breakpoints from before. Okay, low checkpoint, replication count. Let's see the logic here. Replication count is specified only there apparently. Okay, hit F5. Okay, here we are. So this is the sampling part. Let's see how did we get here from low data set. Okay, we are loading the checkpoint. We are grabbing our train data. We are loading the data. Get train sampling ratios. And then sampling selector. So because we are this, we enter here and we set the temperature to 1. So that's where those two are used for the training data set. We didn't hit this for the validation, right? We only hit this for training. So it has to do with the way we sample the batches or something. Let's see. So the function here, what it does is grabs the sizes and then we return this function. Aha. This might be just some weighting logic. How do we sample between different subsets or something like that, guys? This might be literally like, hey, do we sample a bit more from like books versus books 3 versus Wikipedia in the case of language models. I think that's the logic. Okay, let's just go here. So we have the sampling function. If it's not none, then we pass in the data sizes to get the sampling ratios. But how did we get these data sizes? Why 3000 here and 216 here? That's unclear. So we can maybe put a breakpoint there and hit this. Aha, so we have, got it. Okay. So because, okay, this is apparently where the language pairs come into picture as well. So we've picked only these two directions. Shard 0. Let me expand this one. Train split. Okay, we have those two languages. Data sets as well. Epoch. How come this one is so small? I picked deliberately English, Latin, Russian, and Turkish. Both of these should be super high resource, which means way above 3000 sentences if this is what the count gives us. Okay. So then this just grabs the total size. So we'll be sampling proportionally to those. Okay, so this is basically in the context of machine translation. This helps us choose the strategy of how much data we sample from each of the directions. Okay, now this makes sense, but I'm still confused about the actual numbers. And because temperature is 1, this is just ignored. So we just sample according to the number of samples per those directions. That's the logic, guys. And that's the only place where this function is used. Okay. Get the sample ratios. And then once we have that, we just pass those in here. Hit F5, let's see what we hit next. Okay, now we are dealing with the model, but because we are efficient, we go and have it. Just go to FP16. If not CPU offload, then we put to GPU. Okay. And we retrieve it back. Okay, hit F5. Let's see what's the next one. Now we are building the optimizer. All of this happens under the load checkpoint for some weird design reason. Okay, and memory efficient one for RAMs. Okay, configuration of the optimizer. Blockwise, stats, true, learning rate. So there is no mention of this efficiency. Okay. And then there's a config. Let's quickly enter here, just see what it's gonna do. Okay. Okay, hit F5. We are here. Now we are repeating everything the same for this second process. So here we can, let's enter here. Let's understand again why do we get the sampling ratios that we get? Let's enter here. Number of shards. For the split, why would we get only that little, that's weird, guys. Why are we getting only 2 shards for training? We have a lot more shards for training than we have for validation. Okay. Let's enter here. Empty. Sorry guys, just a second. Sorry guys, I had some food delivery. Okay, let's continue. Shard index, length of D for that shard index. And we get 3000. So that's where we get the 3000 from. And we append it. And then we do the same for the second data set. Turkish Latin. This one turns out to be bigger, as you can see here. Okay, let's see why English Latin. If we open up the shard, let's open up Stopes. Let's find English Latin Russian Cyrillic. Here it is. English Latin Russian Cyrillic. Let's grab this one. Copy this. Actually, why are we looking at the shards? Let's go to the retrieve data. Data bin, retrieve data. No, sorry. This is a sharded data set, so it might happen that during the logic of sharding, let's just see, just a second. Let's go to data prepare data, dedupe sharding. Let's find the run. So the sharding logic here was, how do you pick the amount of data you put for a particular, so number of shards. Okay. So we go for each of the shards, we create the data, the outputs, we open the files. Then we append. So how many lines do we put inside here? So we go through the files. Already seen, and we write the lines if we haven't seen them to the target shard. There's a couple of confusing parts there. In theory, we should never, during dedupe sharding, we should never really filter out any sentence, because in filtering we already do language direction deduplication. It might happen that for some reason we have a smaller amount of sentences for a particular language, just because we filter them out because of duplicates, but because it's shard 0. Aha, okay, got it. So I think that's why they do the random logic here, is because otherwise you would always have shard 0 being the biggest, because we always start from it. We pick its sentences, it's never gonna hit the already seen. Maybe that's why they are doing the random logic here with shards, but that's just a tangent on what I'm trying to figure out here. The question is really, why is this so small? That's the first question, and the second one is, why are we picking only? Why are we only picking shard 0 for training. Let's continue. Okay, it looks like the training kicked off. You might experience a bit slower video on your side. It's running. Okay. Not really a super satisfactory answer to my questions. I'm going to stop this. So that's the issue. If I just trigger this run, I would be like, okay, this is training, losses maybe going down, maybe not. But it turns out we literally filtered out like 28 most of the data, because we only use 1/28 if we just use shard 0 out of 28 shards, and I wouldn't notice. So that's why I think these runs are very important initially, just to understand, and then you can kick off the run. So we are close to the moment where we'll kick off and don't think about it unless we see any divergence, spikes, issues, or whatnot. But for now, I really have to spend a bit more time and understand what's going on. Why are we using just a shard 0? Maybe we can ignore some of these arguments like memory efficient setting, which we can maybe analyze just by going through this. We can just basically analyze the VS Code outputs and see whether we figure out anything. But for some other ones, we really need to get to the bottom of it. Memory efficient. So we saw that a part of this is just loading the model as in half precision. But isn't that just half precision? What's memory efficient? What's the main difference really? Let's just filter out 5 files. Okay, you can see here, if it's either one of these, then we have during the load on the CPU. Okay, but that's again nothing different compared to FP16. What's special about memory efficient? Okay, it might just be some legacy flag. You allow some unsupported. Aha. There is no really difference here. Aha. Cast to FP32. If it's memory efficient, then we don't cast when moving to CPU. That's just for the saving to the check. Let's just move to CPU. Okay, so just bunch of different small things like that, apparently. Like this one as well, casting there. But shouldn't this should be or FP16 as well, right? Add effector supports it. Atom supports it. AtomX also. Composite. Atom CPU. Fused atom. Nag. Okay. So we can safely now ignore that argument. Let me just place it somewhere in launch.json where let's find it. Memory efficient FP16 remains there. Okay, I want to understand length pairs really, and how we end up with just 0th shard. That's the weird part. Nice. Look at this logo. Looks like Chrome, but just Ara, the bird. That's our new mascot, by the way, Ara, just because they are very good at mimicking human languages. Let's go to train. Fair6 CLI train. Let's kick off the run. Where is the load checkpoint? I think that's the important part. Load checkpoint, I think we need to put a breakpoint there. Okay, length pairs. Here are the length pairs. Let's enter here. Length pairs. Length pairs. Let's see what we get for this extra language pairs. Empty. So in that case, this should be empty as well. No, Turkish. Source are Turkish and English. Targets are Russian and this UZN language. Sampling is, I guess, the temperature sampling we saw before. Enable the validation. True, whatever that does. Okay. Okay, so it just basically internally now has those languages. That's it. 5. load the checkpoint. Here's where most of this magic happens with iterator. Let's enter here. Okay. F5. Let's find where do we call the training iterator. Okay, probably in here. So I could have removed this breakpoint here easily. Inside of this load checkpoint is where we load the data and the model and everything, and like optimizer. Okay, here it is. Get the training iterator. Train subset. Let's understand why we are grabbing only epoch 0. This is the important piece. Train subset, epoch, combine, data selector, TPU. Let's enter here. Exit. Dude, stop entering all of them. Okay. So load the data set. Let's enter here. Load the split data sets. For the split train, data paths. So we have a ton of them, exactly. And then language pairs. Here are they. So extra data. That's it, language pairs and data paths. So where does the filtering happen then? Oops, accidentally pressed F11. So get the number of data shards. Again, we get all the data paths. We get the language pairs we care about. And then grab the paths, split the paths, get the shard. Okay, let's see this. So files, we have a ton of files here. 1,000 something. And then we go through the files and we go through the split. And if the file starts with train and ends with IDX, in that case, we grab that direction and we add it there. Okay, so direction. We just grab all directions. Let's go back here. So we end up with shards looking something like this. 1728. So English Latin, Turkish Latin is 28. English to Turkish, English to Hindi. So English Russian is actually only, okay, so wait. Turkish to Russian. Turkish is the most present one. Wait. So this was my bad assumption. I thought I'm picking a good direction, but I was not. So English, Latin, Russian, Cyrillic. Actually just a single shard, and then Turkish, Latin, UZN, Latin, same. Okay, just one shard. So there is no error. It's just my misinterpretation of some of our data. Okay, which means that we end up picking this to 1, and this is also 1. Okay, and then we go back. How come we have so little data? Okay, we can now just exit here. This is now clear. So that's how we end up with, so that's how language pairs play a role, and that's how we end up with just a single shard. So language pairs are inside of this multilingual dataset managers. They are basically used inside here. So we have language pairs. And so we only go through those. When we try and get the data, we're only interested in those directions. And so we only pick those languages here. That's how the language pairs play their part in this. And now we just load for only those datasets. We load the data. Let's just quickly enter into load dataset. What does this one do? Okay, get encoder length token, target, and then load from here, train, language, English, Russian. Upsample. Okay, nothing super informative there. Hit F5. We end up with the data set. That's it. And then we go, once we have the data sets, we basically decide how we want to sample them depending on the number of, okay, so now that's clear. We now know what sampling method temperature means, because we have a sampled multi-data set. We have data sets, we have the ratios. We will have the ratios after we basically go over this. Let's just F11 from here, F11, go back, okay. And so we now use those ratios to sample from these two data sets, these two language directions. Okay. virtual data size, split train. Okay, that makes sense. Samples from multiple subs datasets according to given sampling ratio. Exactly. Okay, so let's go back to the long JSON. We are slowly understanding all the parameters. So these two are obviously data arguments. Sample across language directions according to the number of sentences in them. Patch sentences across language directions according to the number of sentences in them. Okay. Save that. Language pairs. We now know how they are used as well. We'll basically be picking only those language pairs, both for training as well as for validation. What happens if we add a pair that we don't support? What if we add a language like English, Latin, Turkish, Latin? Will that break the loading of the validation dataset? Probably it will. Let's see. So you probably need to have both of those, otherwise it cannot handle it. We go to train. Load data. Let's put a breakpoint here. Hit run until we get to here. This should now break, if not even faster than before this line. F5. Let's see, let's put F5 here. Oh, we actually hit this line now. Wait. Okay, this does not fail. Enable, this is set to true. So what does it? Enable M2M and split is in here, and English Latin exists here, and English Latin exists here with the target and the source. Source being English, so this will not exist. So if this was true, then we would go here and do what? We would be adding M2M. English Latin, Turkish Latin. Got it. So because this one is not, got it. So this one does not exist in the shards dictionary for valid. This is, I guess, validation, right? This is validation, yes. So again, we're trying to load the validation one. And because it does not exist, we don't have such a data set, then we attempted to enter here. Neither directions exist. And then we try to go here. And this, if this is enabled, which it is, then we ask whether English to that source exists. Like, go over English. Got it, got it, got it. So he basically tries and sees whether you have some pivot language, basically. And if you have, then for this key, you basically add those shards. Okay, this is mostly like a fallback mechanism. We mostly won't care about this, right? Okay, that makes sense. So we accidentally figured out what this M2M validation means, even though we did not want to do that. And we were not hitting the flags before, so that's interesting. We accidentally found this one out. If true, validate over all training pairs x, x, y, y, given English to x or x to English and English to y or y to are available. Interesting. I didn't see this before. Validate over all the pairs. Okay. Let's move that one. Let me move that argument here. Enable M2M validation. This is, where could we place this one? This is like eval argument. I think going somewhere here. That's how I understand it. So even when we don't have that direction, we are going to validate over English. I'm not sure whether we need that, but I'm gonna leave it. It will not hurt. Okay. So a couple more arguments left to figure out, including replication count. And these three. Okay, guys, this is it for this stream. A lot of insights. I'm gonna take some more time in the next stream to analyze these arguments, and then we'll have to think which languages we actually want to run, because as we saw, I made a mistake. English Russian is not really high resource apparently in our primary data set, which is weird. I'll have to do some analysis of the raw data again. Maybe something weird happened there. And then we can get closer to kicking off the first run. Cool, I'm gonna stop this. I also have to go prepare for the talk, and Niels is coming very soon, guys. If you didn't see it, come to the event happening in like 40 minutes with Niels, giving a talk on will LLMs kill search. So if that's of interest, join us in 40 minutes in the Discord. See you then, guys. Bye bye. Cheers.